It's 1:30 sharp in UK time. I will introduce Dr. Rezapour. Dr. Mohsen Rezapour right now is working in pharmaceutical companies, but I know him back in 2016 when I was doing my PhD at the University of Copenhagen in Denmark. He was visiting University of Copenhagen, and he was associate professor at Shahid Bahonar University of Kerman in Iran. And then he moved to several other places such as Canada, US, and then he left academy and joined the industry. So for those of students who are interested to know what is the life of a scientist outside of university, you can ask those kinds of questions afterwards from Dr. Rezapour. Dr. Rezapour, please go ahead.
Thank you. Thank you so much, Dr. Sadiq Manish. Yeah, as you mentioned, I just left the academy for several years, but still have some research on the industry. The topic that I choose, it's kind of come back for almost 3 years ago when I still working at the academia. The reason that I didn't choose a topic for the pharma is that there is a lot of policy in the pharma, and whenever you have a research, you should be very careful about that. I have some limitation. Maybe in future I can share some of the research about the pharma, but this is a kind of between the industry and academia, and it was about the dimension reduction of the heavy tail data. One of the issue, I will introduce the heavy tail data first, and we'll go through the issue related to the heavy tails, which comes back about the measure of association for the heavy tail random variables, and after that, we'll dive into the high dimensional data. I also had some several other topics related to the time-dependent high dimensional heavy tail, which is come back to the Levy process and its application in real data. And I also work on the ultra high dimensional, but the last two topics maybe we don't have enough time to go through them. Let's start with the heavy tail. When you observe the data, the first thing in the industry you should do is to just plot it, the data. You can use a box plot or you can use a scatter plot. If you use a box plot, as a statistician, the first thing that you should watch is the data that are above or below the max v-square upper or lower bound. We might call it these data outlier, or we might call it extreme. Like, it depends on when you observe such data, you should be very careful about the analysis of these data. There's two reasons that you might observe this data. One of the reasons is about the its kind of error, or maybe you have it as an outlier. Like here for the annual household income, you can see there are a couple of people that have more than 1 million annual income per year. It's not a fake, it's a true one. We cannot call these data as outlier. These are the extreme value data. What happens if we observe the extreme value? If you just come back to some kind of introductory courses in the statistics, when you learn about the central limit theorem and about the application in real world, the first thing that you might see is about some criteria that say that if those criteria holds, you cannot use the central limit theorem. Like here, some of the criteria is for the cases that for the cases of the like here we can see if in the box to the right hand side on the bottom, we can see for the n less than 30, the central limit theorem, it's normally doesn't work, but For the n greater than or equal to 30, you should be very careful, and you should check there is no particular extreme outlier. If you have some of them, you should be very careful because the central limit theorem might not work. That's the thing that we learn in a kind of introductory courses in the statistics. Why? Because the general idea is that if you have extreme value in the data, normally you can say that the variance of the data, variance of the distribution of the data does not exist. And if the variance of the data does not exist, you cannot use the central limit theorem. There is some another theorem that you can use, very old one. Instead of using the central limit theorem, you can use the law for the stable distribution, and it says that if you have independent identical distribution, you can still you have some similar version of the central limit theorem, but it is not central limit theorem anymore. That's the stable law, which says that the summation still converts to some distribution, which we call it stable distribution. It's not normal anymore. But the constant scale is not 1 over n. It means that the mean does not converge necessarily. Some another scale version of the summation is converged to the stable distribution. If we want to compare the distribution, you can see the black one is the normal distribution, and for the different value of alpha, the alpha is indicating the tail of the distribution, which says that if alpha is very small, like here for our case, the alpha for the red one is 0.5, it's corresponding to heavy tail. It means that it has a very fat tails, and it converges to the zero gradually. It's not as fast as the black one, which is normal. For the normal, the scale of the index, the stability index is normal. Normal is also another one of the distribution belong to the stable family with the alpha equal to 2. As you can see, the red one is a heavy tail one, and the normal one is the light tail one. In heavy tail data is almost everywhere. You can observe it almost everywhere. From mathematical point of view, we can define a general class of heavy tail distribution, and we call it regularly varying. The regularly varying distribution are those that have asymptotically the same tail as an alpha stable with index alpha. That's the idea, which means that the tail of the distribution is the same is the same as x to power minus alpha, which is a Pareto, and times to one function that we call it a slowly varying, which means that the ratio of LTX over LX, when t goes to infinity, it goes to the 1. Sorry, it should be x goes to the infinity. I think it's a typo. Sorry about that. There are several properties of the regular varying random variable. I just bring some simulation here. I just simulate from the heavy tail data. One class of heavy tail data that we call it sub-Gaussian alpha stable. And the sub-Gaussian alpha stable has two parameters. One parameter is alpha, and another parameter is sigma, which is corresponding to the scale of the distribution. I use the correlation. Everyone knows the correlation, the sample correlation. And I check if the sample correlation works for this data or not. You can see I just plot on the left-hand side for different value of alpha and different value of the sigma. I generate from the sub-Gaussian, calculate the correlation, and you can see this is a completely close and choice and everything. And this shows that uh, the the sample correlation is not stable. It is not a good measure. It cannot measure the association between two variables when the variables are have heavy tail distribution. What we can do, there's a lot of options here. One of the old one is co-difference, which means that instead of looking at the second moment for the calculation of the correlation, it look at the characteristic function of the distribution. And you can see here the Fermi law is that instead of looking at the second one, it look at the characteristic function. Because the characteristic function is always exists, the codifference is always exists. There are some property of the codifference. I don't want to jump into that. We introduced a new version of the codifference, which called extended codifference. There are some issue with the codifference. The codifference cannot show the independency of x and y when alpha are very small. The extended version that we introduced can show that x and y is independent if and only if this extended codifference is 0. We introduced a way to calculate the to provide an estimation for the extended codifference and codifference for the symmetric distribution, and we also show that what can we do for the non-symmetric distribution. These are some examples that we bring and say that in real data we observe the heavy tail data more often, and I just look at the single cell data and look at the dispersion value of the data and found. I just bring some example here of the distribution of some spatial genes, and show that the distribution of this gene is based on the alpha. You can see here it's a very heavy tail data. The alpha here is 0.36, and for this one is also another heavy tail one with alpha equal to 1.36. Therefore, it makes sense to use this measure codifference for the real example like gene expression data. I just bring some another example for to you for the case if you use the alpha, if you use the codifference instead of correlation. You can see there is a pattern here, and it shows that the codifference has a stable behavior. It shows that it has asymptotically normal distribution. The general idea is that it always exists, and therefore when it exists it has a distribution, and we show that the distribution of the codifference of a random sample from heavy tail data has a normal distribution, and that's a kind of a beauty of this method. And we can use it for analysis. I just bring some example here. I don't want to jump into details because there is a lot of details here, but the idea here is that we use the codifference instead of correlation for clustering of the gene data, and the result, and we compared the results. Uh, we found that there is a kind of a little bit deviation from the well-known package, which is Surat for the gene expression. And the reason for that is that Surat use a lot of other information. We don't use that information. Surat, before classing the data, they scale the data to kill the information of the outliers. We don't do that. There are a kind of a little bit inconsistency between our results and the Surat, but after discussion with the biologists, we found that our result is more reliable than the Surat for the clustering of the genes. The next part of the talk, which is the last part of the talk, is about high dimensional heavy tail data. When you have a heavy tail data, there is a bunch of different methods you can use to model the data. There are one of the famous one is principal component analysis, which is really very old. Although the people may say that yeah, that's a very old one, but still, I believe that that's one of the best method, at least from the statistical point of view, because it's interpretable. But the problem of the principal component analysis is that everything in the principal component analysis is based on the assumption of the correlation. And the problem is that when you have the heavy tail data, the correlation does not exist. And you cannot use the principal component analysis for the heavy tail data. Instead of using the heavy tail, instead of using the correlation, we propose a new method for the, which call it the principal component for the heavy tail data based on the codifference. And the idea is that we first found a unit vector, which is a kind of a which introduce a combination, linear combination of the data, such that it gives you the highest norm. The norm here is that we call it the covariation norm. The norm here is defined by the characteristic function. And for the second component, we want to say that a kind of a unit vector which maximizes the covariation norm, while the codifference between the first linear component and the second linear component is 0. That's almost the same strategy with the same strategy as used in the principal component. If you remember from some of the classical textbook that you might have in your graduation, in your undergrad courses, the principal component is a unit. The first principal component is a linear vector of the data, which maximizes the variance. And the second one is the second unit vector, which maximizes the variance, but the first and second one should have a 0 correlation. We use the same strategy, but instead of using the correlation and the variance, we use the covariation and codifference. After some simplification and some kind of justification, adjustment in the data, we propose the following algorithm and show that this algorithm is corresponding to the definition of the principal component based on the codifference and covariation. To show that if the algorithm works or not, we simulate from the heavy tail data, and in this example, we generate the 12 samples, a 12-dimensional vector, And here, mm, based on we propose the following linear combination. The idea is that you observe these 12 component in real data, but these 12 component comes from 5 independent variable, and this is a kind of a linear combination of these 5 independent variables. Therefore, the task is that whenever you observe these 12, you should find these 5 independent variable. As you can see, based on these metrics that we introduce, the first component will be x1, x2, and x3. These three are in the x1, x2, x3. These one are in corresponding to the one component, which is third. The second component will go through x4, x6, x10, 11, and 12. And the last component will be 7, 8, and 9. These are the components. And based on the principal component, and we compare the result of the principal component and also our method. As you can see here, if we run the principal component, we can see here the principal component have some issue with finding the proper uh, principal component of this data, because the original values are simulated from the heavy tail data. But if we run our method, we can see that our method find the components really very easily and more efficiently, and we show that our method is more robust and more efficient compared to the principal component. I think I should stop here to give the audience if there is any question, and maybe sometimes for the next presenter.
Okay, thank you for the nice talk. If anyone from the audience has a question, please raise your hand. We call your name, and then you unmute and you ask. Anyone from the audience? So maybe I start with some very easy question from a person who is not very expert in biology side. So when you were clustering the genes, you were clustering with respect to what, their sequence or something else?
The idea of the clustering of the gene is that you observe the gene expression of each one, and the idea is that based on the data that you observe, you want to find which genes are more similar to each others based on the gene expressions. And the similarity, the people try to use some principal component. The idea of the surat is just using the principal component. The principal component, it says that those are that are similar to each other belong to one cluster. That's one of the idea, but the general idea is that you have an expression of a gene, an expression and another of another gene, and if these two are similar to each other, these are in same cluster. That's the general idea of the gene expression. Yeah, clustering.
So now my question will be, when you say gene expression, you mean the protein that comes out, or what do you mean?
Yeah, when you do the single cell, that you have a matrix. on the matrix, you have a gene, different genes, and you have the expression of the genes. You have a very huge matrix, and you have a different genes, and each genes have expression. Like you have almost, I don't remember how many, but something like 30,000, and you have a lot of expression for them, and for these the idea is that you wanted to find that which genes are similar to each others.
So we have a question in the chat from Mashal Nagin. I can read it. It says, biological data often contain outliers and batch effects. So how does your approach handle those, especially in the context of highly variable samples like tumor heterogeneity or microbial communities?
Yeah, there's two approaches. One approach is just cleaning the data and cleaning of the data, especially in the surat, just scaling the data. When you're scaling the data, it's almost killing the information of the outlier. We cannot say that it's outlier, it's observation. It's observation. Sometime it might be outlier, sometime it might be extreme value. Yeah, that's the issue. From the statistical point of view, there's two approaches. One approach is assuming those are not outlier, those are extreme value, and using the heavy tail approach. That's one of the approach. Another approach is just assuming those are outlier and just deleting from the data or scaling in somewhere to just minimize the effect of those outlier from the data. There's two approach. We compare these two approach. We compare the result from the surat and the result from our model. In most of the cases are almost similar to each other, but in some cases, our results are different from the surat. I think in the case that our method gives something that are not the same as the surat, from a statistical point of view, we cannot conclude if the result is correct or not. We will discuss it with the biologists and to see if the result makes sense or not. From the mathematical point of view, our result should be more reliable than the principal component. But as you mentioned, if the result does not make sense from the biological point of view, it means that the data that we observe are outlier and are not the extreme. But that's the general idea. That's exploration.
Any other questions? Well, if not, let's thank the speaker and move to the other one. Maybe we can use this React clapping. Okay.